Perfect. Hello, everyone. Hi, good morning and good evening. This is Kalpit on behalf of Converge AI. I welcome you to this webinar where we are going to talk about the plant maintenance and some of plant operations challenges, typically in manufacturing industries, and a few cases in which AI can help uh, redefine addressing these problems and creating solutions that can help the plant operations. I welcome you all, to this webinar, and we'll start the webinar shortly. Before we begin, there are just a couple of quick points that I would like to make. Uh, since the topic is mostly related to manufacturing, if you have any questions or any observations that you would like to share with us, please feel free to drop those in the chat section of this video. If you want to get in touch with us, at the end we'll provide a method to contact us. Of course, you are more than welcome to get connected with us on LinkedIn, follow us on Instagram, and other social media platforms. So with that, I will get started. Uh, we've been working with manufacturing organizations for pretty much the entire existence of Converge, which is almost 7.5 years. But in the last 2.5 years, we've seen this resurgence of applying AI to various problems, and building the solutions. And we've had hundreds of conversations with existing customers, and industry leaders, uh, delivered more than 20 projects in the space. And here is what we have seen, are the top challenges that are faced by the operations leaders in manufacturing. The first is downtime. So why certain uh, uh, plants and certain sections of plants have recurrent breakdowns that keep hitting the production and the overall profit of the plant. uh, why there seems to be always a data disconnect. Data historians collect a lot of data from various sensors and systems from the plants, but having this kind of disparate data produces difficult to act upon and difficult to create insights. Then as the experienced workforce uh, ages out, there are these critical knowledge gaps that appear, which are not covered in the overall knowledge base of the organization. And because of this, there are problems with building this knowledge base and using this data effectively to help in reducing the downtime. And then all at the end leads to planning inefficiencies, where the maintenance schedules and the operation schedules are heavily time based and not condition based, which causes inefficiencies. So this is these are a few examples of the challenges that are uh, typically seen. Of course, these arise from various systems and their interplay. So there isn't a one size fits all kind of a solution to all these problems. In fact, every industry, every plant has a different kind of issue on either of these dimensions. But there are some ways that tech can help address these challenges. So with that, I'll talk a little bit about what happens when you are prepared to address these challenges. So there are very important and very high value use cases that can help and reliably help reduce the downtime, improve the overall efficiency of operations. One of these is using AI for predictive maintenance. Uh, there's this very interesting report by McKinsey that states that worldwide manufacturing could benefit anywhere between 260 to 460 billion dollars in value by 2030, and in fact more than half of this could be specific to certain geographic sectors. Uh, Out of all the organizations that have been surveyed by Baker Hughes, more than 4 in 5 companies have faced more than at least one major unplanned shutdown in the last 3 years. That tells about the scale of the overall problem. There's a typical rule of thumb that is backed by data that 40% of the operational expenses uh, are only related to maintenance of machines, equipments, etc. Now, what McKinsey has said that about 55% of the overall value that is contributed by predictive maintenance can be attributed to just improving the equipment lifespan. So having the right equipment, repaired at the right time, uh, improves and derives a lot of value via predictive maintenance. Again, we can tie this back to the planning aspect, where uh, the maintenance should not be just scheduled, but also condition based, so that improves the overall efficiency of the plant. Another interesting aspect is increasing the equipment uptime. Now, the the equipments that typically fail are because they have been running under suboptimal conditions for a significant amount of time. So if the machine itself can help us understand whether it's running optimally or suboptimally, that helps improve the equipment uptime. We in fact have a case study, coming up in a few minutes, which we'll talk about uh, how this equipment uptime can be improved with predictive maintenance. This is one of the really interesting case studies that we have done in the last year, where predictive maintenance, applying predictive maintenance and proactive uh, actions has delivered more than 30 times the ROI. In fact, within a single month of the system being deployed. Uh, so here, I'll talk a little bit about our customer, and then we'll cover what exactly the problem statement was, and how it was addressed. So here's a bit of the background of our client. They are a very large conglomerate, specifically in the metal manufacturing space. They are spread across 32 manufacturing plants across 9 countries, multiple geographies, and they are in fact one of the world's largest in terms of the annual shipments of product that they do. They serve segments such as food and beverage, automotive, aerospace, and other specialty products, with an overall strength of more than 13,000 plus employees spread out globally. What the challenge that they had was, since they have these multiple manufacturing plants spread out across the world, there was no unified mechanism of addressing uh, and identifying any anomalous operations for their plants. So here is a bit of what we did for them and the overall result that this achieved. Uh, so think of it like this. So there is a plant maintenance at a particular plant. Operations are scheduled to be resumed, the next day. Uh, what happens is when during the resumption of operations, the standby lube oil pump is started. Uh, at that time, as soon as that is started, the gearbox, which is downstream of this lube oil pump, uh, starts raising an alert, and it analyzes the flow during normal operations as well as during plant maintenance phases. Uh, what it does is it identifies the anomalous operation. Uh, Not just that, it identifies that this is not just a suboptimal operation, and it is actually a critical operation flow. This alert is raised to the operations team, and is given to the to the specific team that looks after that sector of the plant. This overall uh, system is configured by the user. The idea is that they understand uh, what kind of uh, operations and what kind of typical parameters a particular system operates at. So they know that a lube oil pump might have slight uh, specific, slightly specific parameters around the pressure, the flow, the temperature, etc. Uh, the main thing here is also creating this kind of a friendly user interface where a user can configure what kind of alerts they would like to receive and from which equipment. So basically, then that can be aggregated to teams levels, so that uh, you know uh, the machine learning models, whatever the predictions that they provide, uh, are converted into the actionable insights and real time information for the operations team. As you might know, manufacturing has very high scale for the kind of cost savings that are possible. So this one AI alert, saving this one pump, saved $5.3 million for our client. Rate, and that critical alert got triggered, uh, and in due time the switchover was conducted and the normal flow was restored, and that avoided the overall problem of replacing as well as the other downstream tasks downtime. Now the interesting part here was, since this uh, alert was highly configurable, uh, the client basically had more than 300 such systems running, and predicting the operations of their equipment. So they could get an overall view of which equipment is functioning normally, where there might be a warning, as well as where that there might be a critical uh, scenario. Not just important to raise the alert, but also to provide real-time analytics to the team so that they can understand if the fixes that they are doing are working, as well as have they had the desired effect on the overall characteristics of the system. With this bit of context, I'll move ahead to the business problems that are typically caused by this kind of a system. Uh, uh, that can be addressed by predictive maintenance, and then some aspects of the solutioning that we have done. Uh, just a short reminder that in case you have any questions, we would love to answer those if you drop them in the chat section. Of course, again, you can always reach out to us and have a deeper discussion where required. Uh, if a machine failure occurs for a manufacturing plant, this could obviously cause production delays, and because of that, there might be the the downstream supply chain effects, etc. A classic example of this is when there are any problems in an oil refinery. Uh, this typically leads to the stockpile of the oil going down, and then that leads to contracts going unfulfilled, as well as other losses of productivity. Uh, there are very uh, clear reasons, if a system goes from preventive maintenance to predictive maintenance, of preventing these kinds of delays. If there are aspects of the overall equipment failure that can be predicted in advance, so that can improve a lot of uh, the challenges and the solutions that are being created to handle those. These might not just be the technical challenges; they might be people challenges, process challenges, as well as knowledge challenges. The more these systems produce data in terms of predicting failures and predicting maintenance schedules, the better they can be built via machine learning, because as you know, the more data you feed to an AI system, the better it gets. Another problem is pretty obvious, that if there are plant shutdowns or equipment failures, that increases costs. It increases equipment costs, it increases personnel costs. It also can increase the overall cost associated with the operations of the plant. uh, there might be customer dissatisfaction, etc., etc. When there are a lot of challenges that are quite apparent when you consider that these equipment failures are central to causing any delays and uh, malfunctions in any plant operations. Here is the overall solution that we created. Uh, Basically, we needed to build something that was global. uh, there are you know uh, 9 plants overall, where this problem statement was targeted for, and they were spread out worldwide. They had very different tech stacks. The data historians might be different, the hardware might be different, the server configurations, the network configurations might be different. Because of the scale of data, there are thousands of sensors uploading with varying frequencies, from 5 milliseconds to 5 minutes, and anywhere in between. So this means that a lot of data is being created. In fact, one of these plants can create anywhere between 500 to 800 gigabytes of data every day. So it is not feasible to run this analysis on cloud, uh, where there might be simply too high costs associated with doing the analysis in more complex data warehouses and uh, data lakehouses. So all of the solution had to be on premise, including the data processing and collection piece. Uh, then the equipment monitoring aspect, which was doing the continuous monitoring using AI. This meant feature extractions. It meant creating the machine learning models to identify the anomalies on a continuous basis, retraining these models, and making sure that the best models were in production at any time. Uh, when these models would generate alerts, it also had to be relayed to the right team, the right stakeholders at the right time, so that they could act upon it. So there was a predictive aspect as well as a communications aspect associated with uh, the solution, which had to be integrated into the existing stack of our client. uh, Converge, in fact, has a couple of accelerators built for this purpose, which power some of the features of the overall solution. The first is called Q2ML, which handles automated model tuning and certain aspects of MLOps, specifically around structured data. And we have Groot, which does rapid backend setup and deployment via templatization. So both of these helped speed up the overall time to solution deployment and reduce the overall costs of implementation. Now, because we have been talking specifically about plant operations and maintenance, one key metric here is mean time to repair. Uh, the uh, the metric itself, can be defined in the following manner. Say there is an equipment, that is operating normally. At 9 a.m., the first failure occurs in the equipment. It has to be repaired, and it takes 1.5 hours for the repairs, and then it's back into operations, normal operations at 10:30 a.m. So the time that it takes for one repair, can be divided into three parts. Uh, Typically, detection of the issue, the time that is needed to just identify that an equipment is malfunctioning. Then diagnosis of the equipment failure. So why has this happened? Are there particular parts, particular aspects of the overall system that are causing this problem, or is it the equipment itself? Uh, so this diagnosis needs to be done, and then the fixing part. So once the issue is diagnosed, then fixing it is the third part of this time to repair. Now, when this kind of issue has occurred over a significant number of times, a typical metric is found, which is mean or median time to repair. The idea is, it is overall, if the equipment was down for 6 hours and there were four breakdowns, so the median time to repair is 1.5 hours. uh, Obviously, reducing mttr is extremely important, so that the equipment is back in action quicker, and the overall equipment availability ratios improve. So we have a very simple demo for you that we have created based on this kind of you know uh, system. So here is what we have built. I'll give a very quick walkthrough of what this is. What we have done is we have created about 1,000 data samples completely synthetically, and I would like to actually show you what that data looks like. So um, let's go with that. Uh, the system overall, is powered with a generative AI model, specifically for building the queries that will retrieve the data. The data is stored in a small database running locally, and the model is basically running on the cloud. Let me show you the data table. So this is what it looks like. So we selected plant A. We have certain equipment types. There are equipment IDs, parameter IDs associated with those equipments. Basically, there are pumps, there are fans, there are valves, compressors. Very usual equipment that you would find in your plant. Now, some of these have raised an alert previously, so you can see the status of the system. Uh, and then there are aspects, such as what was the action performed, what were the notes that were given by the person who performed the action. So let's check out some of the uh, questions that we can ask this kind of system. So let me start with just plant A, and let's see what is the equipment that has been giving the most problems. This is some of the most common analytical queries. Uh, the idea is if we can understand, which equipment typically has the most problems, and then how much time is spent in repairing that. So this is in analyzing this. Uh, so what we can see is pumps have generated the highest number of alerts. Fans have produced 87 alerts, and valves have produced 86 alerts. If you want to actually see this breakdown, so we have a simple chart handy which says the alert count versus the equipment type, and you can see very simply what kind of levels of alerts each equipment has generated. Now let's ask some kind of follow up. So what are the most common issues or alerts raised by pumps? Now, while this is happening, let me talk a little bit about the the data itself. So let's go back and check out the data again. So ideally, at plant A, what we have seen is typically there are pressures as parameters, then flow as parameters, vibrations as parameters, and each of these is sensed by a different category of sensor. When we say the finding the most common issues, every equipment can fail in a different manner. It is very important to understand based on the parameter category which kind of failure it is, and then planning for it. So let's go to the answer. So the pumps typically get vibration alerts. This can mean misalignment, imbalance, or mechanical looseness. Uh, right after that are pressure alerts, and pressure alerts are typically blockages or leaks, which are very critical problems in the overall operations. Let's visualize this super quickly. So we can see that temperature and flow issues are the second last and last, but vibration and pressure are the most important parameter categories, specifically around pumps. Now let's talk about what are the resolutions. So what are the top res- resolutions for uh, pumps that have vibration alerts? Um, so what we intend to find is historically, if there has been a set of pumps that has malfunctioned at plant A, how has that been historically addressed? uh, is there a clear pattern of those fixes, and whether that can be applied to other plants? So what we can see here is the component replacement is and no action required are the most frequent resolutions. Both have occurred 7 times. In fact, this could mean that component replacement is happening a lot of times, and that could define policies around procuring as well. What you can also see is there are a number of false alarms. So it needs some refinement because there are a lot of false positives in the system as well. If we again visualize this data, so we can see some simple analysis of this. One last aspect that this demo intends to show is because the data also contains manufacturer details. So what we can do is list of pump issues uh, by manufacturer. So what we intend to do here is we want to understand how many problems each pump manufacturer uh, each pump by a particular pump manufacturer has over a period of time. Uh, so I'll quickly show you the kind of data that we are looking at here. So here is the manufacturer. There is Rockwell Automation, there's Siemens, etc. So yeah, so the answer that we have, is Rockwell Automation, has two entries. Philips has a particular, is now in an okay status after the suction line blockage clearance, etc. And we can actually visualize this as well. So, Rockwell, because, this is uh, probably the most deployed in the plant, has, the most equipment, uh, you know, uh, malfunctions, whereas others have one malfunction each. Uh, what we can also see is there are certain alerts and advisories suggesting that there might not be an immediate issue but need to be monitored. This can also help inform the kind of quality of these equipments for downstream tasks. So that's the short demo and presentation that we had. I would love to catch up and know more about what problems you might be facing in your plant operations. Here are some of the key categories that we have seen challenges in, and the opportunities that are presented by AI. For example, production and maintenance schedule optimization, real-time sensor intelligence, predictive inventory management, and even vision AI and defect prediction. Uh, there are a few case studies outlined here, and these are available typically on our website, which is converge.ai. Uh, that's it, for this webinar. We also have an interesting accelerator that has been uh, put on Azure Marketplace called Data Lens. It is a generative AI accelerator that integrates with your existing data and abstracts away the complexities of generative AI implementation. Uh, Thank you, for this great webinar and watching this with us. It is a pleasure, discussing the uh, challenges and possible solutions for plant maintenance. And we would love it if you connect with us. I'm Kalpit Bhavalkar. See you soon. Thank you.